let's think some more about these electromagnetic forces on our secondary loops and how this pushing or pulling of the secondary loop by the primary wire reinforces our understanding of Lenz's law. So here, in this example, we worked out that if I1 is increasing, our secondary loop would be pushed away from the primary. And here's another way to think about that or understand that phenomenon. If I1 is increasing, that's creating increased flux through the secondary loop. And we know from Lenz's law, from the idea of electromagnetic inertia, that the system will respond to try and oppose that increasing flux through the loop. And by being pushed away from the primary, by moving away, it's moving into a region of lower magnetic field. So in trying to oppose the increasing flux through the loop, the forces sort of conspire to arrange to push the loop into a region of lower flux. Likewise, over here, if the current here is decreasing with time, then the forces conspire to pull our secondary loop towards the primary. So if the current is decreasing, that means this outward flux here is decreasing with time. The system responds by pulling the loop into a region where the outward flux is greater, where the B field is stronger, closer to the primary wire, helping to restore or replace the flux that we're losing because that current is decreasing. Okay, so that was another way to think about these pushing and pulling effects. Let's now get into the mathematical detail of computing these forces on the loops. Let's start with trying to find the electromagnetic force, the Philb type force, on this bottom segment of our secondary loop. So this will be IL cross B. This is I2, the current in that wire segment, times this L vector. And L vector will have a magnitude equal to the length of this segment, which we've been calling W, and it'll point in the direction of S hat. So our S hat vectors point kind of counterclockwise around this loop, so S hat points this way. So L points in the direction of a positive current. So if I2 is positive, then I2 would be pointing in this direction, in our S hat direction. So hence the agreement between the vectors, these two vectors here. Okay, so L cross with B1, this is the magnetic field produced by the primary wire at the location of this secondary, at this segment of our secondary wire. So the L cross B becomes this. We need to do S hat cross with B1. So S hat is to the right, cross with B1 upwards. That gives us a downwards pointing electromagnetic force. If we throw some axes on here, say the X and Y axes, then crossing these two vectors gives us a force pointing in the negative J hat direction. So there's our cross product, negative J hat, and we've got I2 times W, the length of that segment, and then times the Y component of our, or times the magnitude of B1, which you know from Ampere's law is given by this, mu naught I1 over 2 pi A. So as long as I1 is positive, then B1 points in the K hat direction, and we have our S hat crossed with K hat gives us negative J hat. All right, so that's how our vectors and signs work out for this expression here. Note, for the strength of the B field, I've put in A here for the distance away from the primary wire. This radial distance there is A. That radial distance away from our primary is B. Okay, let's check our signs here. So this is saying that if I1 is positive and I2 is positive, so if I1 is positive and I2 also is positive, meaning pointing in the S hat direction, if they're in the same direction, we know they should attract each other. So if I1 and I2 are both positive, then we should get a force on this wire in the negative j hat direction towards the primary. Okay, so that checks out. If, on the other hand, I1 is positive but I2 is negative, so if I1 is this way but I2 is that way, then we know that these two parallel wires would repel each other. So if I1 is positive and I2 is negative, this negative times that negative would give us a plus j hat force on this segment of wire, pushing that segment away from the primary. Okay, so that was all just double checking that our signs work out here. Let's write a similar expression for the electromagnetic field type force on the top segment of wire. So this will be I2L for segment B crossed with B1 at segment B. Up here, ds points to the left, so our s hat vector points to the left, so L here would be W times that s hat vector, so this L points to the left in the direction of a positive I2 in that segment. So that crossed with B, that IL crossed with B points upwards in our plus j hat direction. So our cross product gives us a plus j hat over here. And then we just have I2 times W times our magnetic field strength at that location, which again comes from Ampere's law. So mu naught I1 over 2 pi B. Must keep track of the two different currents here. This is the current in the secondary, but the B field is being produced by the primary. So here is the B field produced by the primary, which depends on I1. I1 is producing that B field. I2 is responding to that B field. Let's check our signs here. This says if I1 and I2 are both positive, then that wire, the top wire, should feel force in the plus J direction. So if I1 is positive and I2 is also positive, this is the positive direction, the DS direction for I2. Those two wires carrying opposite currents should be repelling each other, so the top wire should feel a force in the plus Y direction. That's exactly what this says here. So our signs work out. All right. If we want now the net force on the whole rectangular loop, we need to sum these two. So let's find the net force in the y direction. That'll be the y component of the force on segment A plus the y component of the force on segment B. So we're adding these two expressions here. We see that they're identical to each other except for this difference in sign. And this is a 1 over A, and this is a 1 over B. So adding those two and factoring out the common factors, we get this. There's a mu naught W over 2 pi that comes out. I1, I2, the product of those two currents. And then there's this. Note that since A is smaller than B, this term is positive. And then there's that negative sign sitting out front, which came from this negative sign up here. So again, let's check that if I1 and I2 are both positive, so I1 and I2 here, I1 and I2 are both positive, then these wires should attract. I1 and I2, they should attract, so we should get a net force in the negative Y direction. This bottom segment should be pulled down towards, or the whole rectangular loop will overall be pulled down towards the primary. Okay, so now let's take our solution up here for I2. We've worked out at great length how the secondary current depends on the rate of change of the primary currents, and let's sub this whole thing in for I2 in this expression right here. And that way what we'll find, after some simplifying, is an expression for how the net force on this secondary loop depends on I1 and the rate of change of I1. So here we go. There's I1, and subbing in for I2, this expression, which we worked out earlier, depends on the rate of change of I1. Let's collect terms one more time. So let's see here. Note that I've got mu naught over 2 pi, so there's two factors of those. Here's a W and a W. There's two factors of that. I'm going to collect all the geometric terms with the B's, the A's, and the W's. Oh, and this negative sign and that negative sign will cancel. Simplifying to this expression for the net force in the Y direction. We have our constants out front, Then the sort of electrical part, the net force depends on I1 and the rate of change of I1 and the total resistance of our secondary loop. And then here I've collected all the geometric factors, the parts that just depend on the dimensions, the lengths and widths and position of that secondary loop. And we see that if I1 is positive and increasing, we'll get a net force in the plus y direction. So if I1 is positive and increasing, then our secondary loop gets pushed away from the primary. If I1 is positive but decreasing, the net force would be negative and our secondary loop would be pulled towards the primary. And any other combination you could think of. If I1 was to the left, for instance, if I1 was negative, but then diminishing in strength, so this derivative was positive, then we would get a net force that was negative. So if I1 was to the left but getting weaker, then our secondary loop would be pulled towards the primary into the region of stronger field to replace the diminishing field that was coming from I1 weakening. Okay. Big picture, what we now have is a way of controlling the movement of that secondary loop. If we can control this current and its rate of change, we can push this secondary loop away or towards us. We can push it around. We can exert forces on this object, which will have mass. This is some object that we can push around just by controlling the current in this wire. What we have here is a motor. We now have the basic physics for making a motor work. It all depends on electromagnetic induction. By controlling a current, it's the current itself and the rate of change of the current in some primary, we can exert pushing and pulling forces on a secondary. We can move objects at our will with electricity. To conclude here, or sort of an extension, a lot of this was predicated on, or some of this was predicated on our assumption here that A and B were going to be fixed. We looked at the forces exerted on this loop, but we're actually thinking of the loop not being able to move, like being nailed in place, not time dependent. But if we want a motor, then we do want this loop to be able to move. We want to be able to push this loop back and forth, doing mechanical work on it. So that means that A and B are not going to be fixed. A and B are going to be changing with time if we're physically pushing this loop around. And if we allow A and B to change with time, we have to make some alterations to our calculations. If the loop is free to move, then A and B both become functions of time, and we have to go back to step 3. In step 3, when we took this time derivative of the magnetic flux, that time derivative acted only on current 1 because A and B were not functions of time. But if A and B are allowed to change with time, if the loop is allowed to move, then these are functions of time as well. So this time derivative needs to act on both I1 and B and A. So that means back at step 3, here's what we would have to alter. We would have the opposite of ddt of the magnetic flux, which is a function of time, and of A, and of B, with A and B both themselves being functions of time. So the opposite of ddt of this, here is our magnetic flux, where we've got time dependence here and time dependence here. So taking the time derivative of this thing, we have to pull out the constants, mu naught 2 pi and w, but then chain rule. So we have di1 dt times the geometric factor plus I1 times the time derivative ddt of this geometric factor, the time derivative of the natural log of b of t over a of t. And this whole expression, with this extra term allowing for A and B to vary with time, this whole expression would now get inserted for I2 as a function of time. This is I2t times r, so we could divide through by r. And this whole thing with the divided by r right there would get subbed in for I2 of t in our net force equation. So this would go in right here for I2. It would take the place of this expression in the blue brackets if A and B are allowed to be functions of time. What a ride.